然后这上有一个小的这种一亮一亮的这样子那种。
啊，好的。
很清楚，我听你的声音。你要是加上麦克就好。
Hey guys, you guys gotta behave because can you mute your phone because it's
Cool.
okay.
对，最后就把它直接。
You haven't mute. Do you mute? You need to mute.
I can mute myself.
Yeah,
Yes.
yeah. Okay. Okay, it's much better. Okay. Main. Okay. So for now on, when we have all the lectures, it's going to be record. Okay. So whatever I say, whatever you behave, it's going to be history, because we might get replay. Okay. For example, like me in focus, that's not good. Okay. All right. Min, can you just sit back? Okay. So we have a big plan in this summer. Okay. So right after this class, let's make sure you guys can log into RoboGyms and make sure you guys have an account there. Okay, make sure you guys can look at this teaching materials and make sure that you guys can do the programming homework. We have about we have 20 tasks here. Depends on what level you are. You're going to take different tasks here. Okay, each task here is one programming project. Okay, so in each project we have a different engineer points, right? So if you guys want to say who is the best programmer here, I just add up all the program you finish and what's the engineer point associated with it. I immediately know who's the best programmer here. Got it? Got it? So we have 20 projects. Each project has engineer points. Okay. So when before the season starts, I just look at each of you. Right. That adds up the engineer points. Okay. So let's have a broad overview what we want to do in this summer. Okay. In this summer, we mainly want to has first a couple sessions. Some of them you already know it. Some of you you don't. So depends on the group progress. Okay. Even some of you might already know how to do it. We will give you even more challenge tasks to do. Okay. So we want to keep every people in the same pace. Okay. First, we need to teach you how to. First, we need to teach you how to assemble the. What's that? How to assemble the. No signal. Power off. Hold on. Do you hear sound? Maybe if not, it's just something. It drops. Okay, just display problem. Okay, guys. Okay. First of all, we will teach you how to connect all the pieces together. So last year I did a lot of things for you. Okay, you guys think connect everything piece together is easy? It's not easy because I did quite a bit work for you. I set up everything right for you. So you guys just need to do a plug and play. From this class, look at how many robots on the back side. We have about five robots there, right? Right? None of them connect to the phone, connect to the they call expansion hub, right? So you're going to split into say 5 groups. You guys volunteer to make a partner, find your squad. Okay, split you guys into 5 squads, and you guys volunteer to form training squads. Then we're going to piece everything together from scratch. I'm not going to help you. I'm going to teach you how to do it. No matter what issue you run into, for example, you have a failed connection problem. Then they need to write a report. Say we cannot connect to the expansion hub. Then we need to find out why. And you need to broadcast your findings to the rest of the squad to say, hey, we have this issue. So this is called knowledge sharing, okay? Because when we reassemble the robot, all the pieces, they are in random state. Some of them already set up, some of them is misconfigured. So when you put pieces together, different squad will run into different problem. Some squad have a cell phone problem, some squad has a cable problem, some squad will have a configuration problems. None of you will have the same problem. I would say may have same problem, but you will run into a lot of unique problems because all the pieces in random state. Whatever the state we detach from the last season. Got it? Okay. So you need to share your knowledge. Once we teach you how to do the assemble, then we are going to refresh your memory about how to do the job. Question? You're welcome to do so, especially for the issue you run into. This is supposed to go to the pre-season training. Pre-season training also belong to the engineering notebook. Okay? You did, but you're not from the beginning. Mm, you will know when you after today's class, we will try to assemble everything together. You will not run into your. What do I mean is, I have a lot of missing pieces. Okay, so so now after that we will teach. How many of you know Java? One, two, three, four. Okay. So Elena, do you know a little bit Java? All right, that's fine. Okay, well, that's good enough. Okay, Java. And here we are not supposed. We will maybe host a different class for serious like a Java programming. But here we will teach you whatever the Java programming surviving skills. This is whatever you need to know, and we can teach you Java pieces one by one. We are blending the Java programming training in the rest of the projects. Okay, so we will teach you how to do the programming, how to load the load the program to the robot, and after that, this is what we're going to do. First, you need to know what's the manual control. Okay, then we're going to teach you how to control the robot use a feedback loop. There's a lot of sensors, right? Like encoders in a motor. That's a sensor. It sends how far the robot goes, right? And there's a gyroscope. Detect what? Hey guys, gyroscope detect what? Orientations, right? What can we use gyroscope for? Detect turn. We use that to control how many degrees the robot turns, right? Right? And then in last season, what else? What kinds of what kinds of sensor would we use? What? Camera? What the camera can do? It detect what? It it detect object positions, right? Positions on the screen, right? Right? It also tells you how far away, right? Oh no, it only tells you where it is, right? In last season, we didn't use the uh, Euphoria. Do we use the marker images? No, we don't, right? If you use marker images, you know the relative position of the robot to the image. So we have to. Last year, if you use Euphoria, we actually were more robust. Okay? Slider? Encoder. Because your motor drives the slider, right? 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 So, and what else? There's a couple of sensors we didn't use last season. We never use any distance sensor, right? Ultrasound sensor. Ultrasound is ultrasonic sensor, it's basically like a bat. It's based on the beam back, the echo of the ultrasonic. You know how far away, right? Actually, ultrasonic sensor has a really good position, a very good sense accuracy. It can detect something plus or minus like about 2 millimeters. Okay, it's very precise. Okay, 5 meters, 5 meters. Okay, our stuff is about 10 meters. Right, that means as long as it's half the field, you know it, right? So we also has we have a lot of sensor there. Also has a short distance sensor. It's basically use infrared. Yeah, proximity. It basically is a user infrared sensor, right? You send out infrared. It's based on beam back, right? So you basically we will teach you how this signal, how those sensor works, okay? And we will teach you about a little bit about that, but the majority of the focus is on how do you write a program to write a feedback control to let uh, robot do something. Let's look at a couple projects you want to do, okay? For example, move exact distance back and forth sideways. What sensor to use? Yeah, encoder, right? Okay. Turn robot in degree by encoder. You need to do calculation, right? You can turn robot by say 30 degree with the input of what's the wheel base, what's the wheel size, right? You can do geometry calculation, you know how many degree you turn, right? You also can turn in degree by gyro. Is that right? Okay. And the thing we didn't do last year, actually we paid big price for it. Our arm keeping falling off, right? Why? Because when the arm reach limit, we still pull it. Huh? No, we didn't respect any limit because yeah. Do you know why? Yeah. Do you know why it doesn't work? Because encoder, in order to say you move arm, say you set a limit, say your arm only can move 2 feet, right? But with a 0 point, the encoder only give you a absolute value. It doesn't give you a relative value. If you say move by 2 foot, and where's the 0 point, right? Since we keep banging back and forth, we don't know where is our reference point. As a result, we don't know move for by 2 foot it is, right? Right? So we are supposed to use touch sensor. What's the touch sensor used for? There's a button. When it's got activated, let's get a touch sensor. You need to put all the sensor together, okay? This is another thing we need to do. You need to put the sensor together, such as easy to find, okay? So, yeah. Touch sensor is very simple, okay? It basically is a button on the surface. Oh. You need to put your headset back on. Yeah. Yeah, right? There's a button on the surface, right? For the mechanical side, you need to basically mount this thing to the arm such that when you do, there's a two purpose use of the touch sensor. One purpose, it is you know where is the zero position of the arm. That means when the arm is fully retracted, right? When this is activated, that means you need to write down the, the at the moment this thing touch it, write down the encoder position as a reference point. This is a 0, right? Right? This is called calibration. That means you use touch sensor to do calibration. No way it's a 0 point, right? And you need to another sensor on the other limit, right? When the arm is fully extended, you activate it to cut off the power. Or just say hold there. You cannot move that point, right? So with that means in order to achieve the arm range checking, how many touch sensor do we need? Right? You need one. Yeah, one for minimum, one for maximum, right? So yeah, so in that case, it not only need to work on the programming, but also need to work on the mechanical side. You have to make sure this thing, the limit switch really can represent the min and max, right? If this thing never trigger, you still have the problem, right? So now we reduce a lot of problem. Last year we say, oh, arm falling off, right? Okay, that's really important for robustness and accuracy. For example, in last year, no, in what do we call vortex? It's not vortex. Your velocity, vortex? Not the velocity. What's the yeah, rally recovery? Not the rally recovery. Just last year, before. No, no, before Ruckus. What's that? Rally recovery. Okay, it's rally recovery. So basically, yeah, yeah. Basically, in autonomous, autonomous, you need to put in those blocks precisely, right? You need to know which level is it level one or level two, or level three, right? So in that case, you need a very precise encoder calibration for the arm. Right? Otherwise, you don't know, right? Just let it drop, right? A lot of things just say I will always go to the maximum distance, let it drop to the bottom, but that's an issue because when you drop, it's very unpredictable. You could bounce away. You could jam, right? Right? So basically, okay, stop on with the touch sensor and extend. If you can achieve use touch sensor to the calibration, then you can program extend arm by distance very precisely, right? Got it? Okay. This is basically one thing built on top of each other. And okay, let's detect an arm moving range by touch sensor. And how do we detect wheel jamming or wheel is losing? Last year we paid a price. The motor is just spinning crazy and we don't know. And the robot just go crazy and spinning around. How do we detect that? How do we? High resistance or free spinning. How do we detect the motor is free? How? 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 What kinds of logic? Tell me the logic. Hmm. Yeah, exactly. Right? Right? So in this year, we're going to last year we only everything's open loop. You just go to this place, right? The only feedback loop we do is PID control. The rest of thing, everything we call open loop. Open loop is means you ask a robot to go somewhere and you never check you go there. You just say, oh, moving by 5 step. You just blind for the moving 5 step and you never check, right? Right? But if you really want to check, you have a problem because you have to totally rely on a sensor. So for example, if you ask you to go like 5 steps, but your body memory mess up. You always you walk 5 steps, but you only remember you walk 4 steps. So you always get wrong. If you have a feedback control is wrong, right? Right? So that means even the open loop, that means you never check your by feedback, right? It is not reliable, but it's simple, right? If your device is very reliable, for example, your encoder never fails, it's not an issue, right? But usually people will go to feedback loop because you can mutually check. You not totally just count on one. If you only count on one, like our last year, we have a problem. If the sensor fails, then the result is wrong, right? And in this year, we're going to use multiple sensors to check. I will teach you how to do it, okay? So if you check multiple sensors, then things is complicated now. Say for example, like we just say, the you depend on the encoder and the gyro to say whether the motor is wrong. What if the encoder is bad? Then you have to then that means the motor is not fail, but the encoder is wrong. Then you think the robot doesn't go to the place, so you mess it up, right? So then it can detect use metal. Mm, for a couple of years they didn't use that at all. Okay, so that's why we only back up one or two. Okay, so let's go to the topic. So now you have a multiple sensors. How do you decide what's the true answer? If the answer from different sensor is different, if answer from many sensors is different. Okay, so one way to do it is you cannot count on two sensors. If two sensors, so one of it is wrong, then you are confused, right? 50-50, right? Right? Or you build up some statistical model. Say sensor one will fail, has higher frequency to fail. Then you will trust one of them, right? Right? So even you have two, you still have a weight, right? Right? So basically we will teach you a couple of strategy. How do you make decision? Okay, if something gets wrong. Got it? Okay. So this is basically called multiple sensor control. All right, you have multiple sensors. How do we control it? Right? So you have to basically need to learn how to program this thing. We only can teach you basically high level concept. Well, hey, we just do voting. One to one, the voting is a one to one voting. If you have two votes, right? If you treat it evenly, you have a problem. You have a proper statistical model to say let's vote differently. Then how do you set up the probability? How do we measure it? If you dig through if you're following the thread, how do we implement it? If you find out you have a lots of issues to solve, right? You cannot just come up with arbitrary number to say I will trust say Tyler more than the Jermaine. How do I trust this? How right? Right? We need an observation, right? One way to do this is very heuristic. Say, oh, my gut feeling test that I will trust uh, trust like person A more than person B. I will 60% chance I trust Tom, 40% I will trust like a Mike, right? Right? So this is your gut feeling. But where's your gut feeling comes from? Where's the gut feeling comes from? Because subconsciously in your mind, you are doing learning. Okay, you just don't know. Your your you have a neural network in your brain. There's a AI coming on recently, right? Question? Continuous bell system? Mm, yeah. Yeah. Did you see the one of the one of yeah, they use the two bells to suck in the use a tank track. They use tank track to do yeah. Uh, uh, uh. Okay, good. Okay, so basically, even we give you a high level concept, and you need to follow your thinking. Okay, all the way down to how you implement it. You will find out whatever you practice in during this programming stuff, it's actually you're going to learn in your school. Probabilities, right? Likelihoods, optimization problems. The other thing is optimization problems. This is it's totally related to a feedback loop. For example, in order to find out, um, in last year we are, how many of you know what is PID control last year? You sort of know it, right? Because PID control depends on the observed error, the value of the error, okay? And make decision how much feedback force you're going to compare, say, for the arrow, right? What? PID has a 3 terms, right? P is proportional. Mean, can you explain it? Right?
So basically, it's proportional, integral, and derivative terms, and it uses all of them. And you give them specific numbers to multiply back to figure out how much power you eventually control the system. And the proportional one is just like calculating like from like let's say you want to go you want to have a proportional acceleration, right? Just do that. But I think the integral term is so that you don't overshoot or something, and then the derivative terms is so that you don't. It is so that you slow down. You slow down before the end. So it's complicated.
Actually, it's not complicated. I give you 3 sentences. You understand immediately. Okay. PID is just look at the 3 terms. Okay. P, it is look at your current condition, your current position, and your feedback control is proportional to the current arrow. Okay. Say if you miss 5 steps, you're going to apply 0.5 power, right? If you miss 10 steps, you use 1 motor power, right? Okay. All right, let's use 3 sentences to P, it is look at your current arrow and make a decision. Okay. I is integral. It's look at your history. It look at the whole history and make decision. Okay. D, it is look at the trend, trend. Yeah, derivative, right? So P proportionally look at the current arrow, the current based on your current situation, make a decision. Integral is look at your historical information and make a decision. And D, it is look at the trend. So look at the future and make decision. I give you a more example. Say I always like to use like swimming. Say if we go to a swimming coach, okay? So you go to a swimming coach. The coach find out you have a target to say for 100 meter. For 100 meter, how much you can? Anybody do swim? 1 minute 30 seconds. Okay. Say suppose I'm the coach. You come to my place. So I do your color measurements. So you are the 1 minute 30 seconds for 100 meters. So I want you to improve to like 1 minute 15 seconds. I want to improve 15 seconds. Okay. So I'm saying based on your 15-second gap, I think you should come to my place to training for 2 hours per week. So you can improve in a 1 month time frame. You can improve to 15 seconds, right? So this is called P, proportional. So if I set your target to say you have to improve to 1 minute, okay, like you have to count every day, 8 hours per day. All right, to get trained to reach your goal. Got it? This is proportional. Okay. Integral is like this. Okay. Say suppose Jermaine has been he is my student for like a year. I know how fast he can learn, right? Right? I know you usually if you say you come here for 3 months, in the first month you said you want to reach improve by 15 seconds, but in first month pass you only improve by 2 seconds. Okay, right? So in the first month I say you come to my place every 2 hours per week. 1 month pass, you only improve by 2 seconds, but you need to improve by 15 seconds. What should I do? Yes, because look, at least look at historical information. You didn't improve based on this. It's still gap, still long. Then I will say, hey, okay, I increase the power. So you have to come here for 6 months, 6 hours per week, right? Right? Basically, I look at historical data and make another projection, correction. Okay. Okay. Now let's go to the his trend. So suppose Jermaine come to my place for 2 months. Okay. First month he improved by no. First month he improved by 5 seconds. No, by 10 seconds. Okay. And the second month, he improved by another 5 seconds. Okay, I see the trend. He's getting there. He's getting there, right? So probably in the first month, I teach you, you come here 8 hours per week. Okay, because we'll look at the trend. In order to reach like improve 15 seconds, you don't need to come 8 hours per day, right? So that means I can cut your feedback loop. You don't need to cut 8 hours a day. 1 hour, 1 hour per week is good enough, right? So this means I look at the trend, right? To do this, right? Right? So this is 3 words. P, look at the current information. I, look at your historical. Integral actually is historical, right? D is a trend, okay? Derivative.
So like you derive the past.
Yeah, yeah, right? This three information, right? Let's give one example. So if you want to implement like a car at a cruising speed, cruise control, right? And anybody tell me why the eye control is the historical control is very useful. Why? Mean?
So so that you try not
It's not overshoot. When you go up slope, right? F-
okay, so I think
For example, yeah,
look how fast it accelerates. So it makes you like accelerate less.
yeah. I just yeah. For example, for example, you do a cruise control. You want to set your speed at 60 mile per second. Okay?
Per second?
60 mile per hour, right? But your current speed is 20 miles per hour, right? That means based on this calculation, you say I need to do a half throttle to reach the acceleration, right? Right? But this calculation at the leveled ground is good. If your car sit on a slope, half throttle probably is still going backwards, right? How do you detect it? Detect it is you set to be half throttle, right? You monitor it. You find out after 1 second you go backwards. Then the eye control will kick in. That means I need to speed it up more. I probably do full throttle, right? Got it? Right? And the the future control is very important. Why is useful? It's useful when you go downhill, right? You apply big force, but find out that you overshoot too much. You will cut off the power, right? Right? So this is just refresh memory, right? I guess a lot last year I talk about so many things like this. You guys say, huh? Right? But once you implement it, when you actually tweaking the PID values, right? You guys understand what I'm talking about. How many of you tweak a PID last year? Mean Helena, do you tweak it? Okay. This year and last year the PID value I gave to you is approximately right. Okay, you don't need to do a lot of tuning to get it right. This year I'm going to give you everything out of whack. You have to, okay, you have to learn by yourself. Not right. Last year the PID control is relative to the mass of the robot. I mean, this year everything is different now. You got different robot.
Yeah, yeah, correct. Yeah, I mean you get kind of close.
All right.
You'll just make the weight the same.
Okay. I think you guys are smart. Yeah. So so basically find a way to figure out. Okay.
First proportionate and then like try to like tweak it after that.
Okay. So then let's go to the next project we'll talk about. Then,
Who needs PID? I think you have to do like complicated Laplace transforms. Yeah, Jermaine.
that's overkill.
Right?
Okay.
Can
Okay.
you send me the audio recording? I have to make a bunch of memes.
Okay. Good. Let's Okay. Hello. Hello. Okay. Okay. So another things you guys to learn it is so far we already talked about in this summer program we teach you how to control a sensor, how to build out a feedback loop, use PID control, right? Right? And use multiple sensor more probably, right? How do you build up feedback control? Another dimension is how do you vote for multiple control? multiple sensors, right? You can learn. The third thing you're going to learn is how to do optimizations. So when you guys mean how painful is to tweak the PID value?
Uh, wasn't too bad.
Okay, tell everybody how do you do it
We had to put in different values.
and how do you try it?
That's so painful.
Yeah.
Would you rather do the math? Yes. The math is very complicated. Doesn't matter. I was reading it said you had to do like a bunch of soft transforms to find the equation.
Well, whatever. There's a lot of trick to it. Okay. Okay. So and this year we're going to teach you one more thing, a level above it. How do you write a program to find it out? What's the best
I think there's software that lets you find stuff.
software? Last year we only do the grid search. We just
It's on GitHub.
we do grid search. We know the proximate range and we split it into a couple of sessions and tried it out one by one, right? Right? So for example, hey, okay, let's have some high level concept first. Anybody know what is grid search? Grid search is say, for example, somebody missing the wood, okay? He's got hurt that he doesn't cannot respond to your phone call or anything. So how do you do the search? Say suppose you have 10 people, right? Or 25 people, right? And the area, say the forest is a rectangle. How do you do the search? You will split the forest into 25.
Someone could like get hurt.
Okay. 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 Yeah. Okay. So so basically, guys.
Natural selection. You're assuming it's a guy. It's a natural selection, and you gotta bring in a forest. So
Okay. So the basic idea is very simple, right? You divide and conquer. You split things into a couple of sessions, and every group, every squad look at each session, right? And find it out, right? Okay, got it? Do do you guys know what's the issue about this? Say because this guarantee you will find the answer, right? The problem is grid search. They call it a curse of dimension. Anybody know what's the term called curse of dimension?
the larger it is, the exponentially harder it is to find it.
Yes, exactly. It's not larger. It is no.
Smaller, so you have less area.
Hey, let's give you one example, right? For example, when we do PID control, right? We need to set at least the three values. We're trying to find in three parameters, right? Right? We need to find the value of P, value of I, value of D, right? The scaling factor, right? That means you need to search for three values, best values, right? How do you do the search? Say you you select a range which like zero point 0.1 as an interval for the P, select range 0.01 for the I, the several range for 0.12 on the D, right? Then you have to search all the combinations. That means if you have a three, you need to try out three P values, three I values, three D I values. How many times you want to check? You have three P value to check, three I value to check, and three D value to check. How many combinations? 27, right?
But that's not even really good because you want to search all the values possible.
Yeah, yeah,
Faster.
yeah. So, right? So if you want to say right now, you just say every one, you only try three, but usually that's not good enough. You cannot find the best value, right? Now, how do you do the search? You're going to refine it. So I'm say to speed it up, I'm going to find, I'm going to try 10 P I values, 10 I values, 10 D values. So combines what? It's 1,000. You need to try 1,000 times.
Is it possible to do binary search with PID?
Huh?
Is it possible to do binary search?
Let's go to that later. Okay. Okay. Yeah, yeah. So basically, if you do 10, 10, 10, then it's 1,000. If you want to try 1,000 times, you cannot make it, because before the robot can try 1,000 times, the battery dies, right? So then how do you do it? So because every battery, because when you do the tuning the PID value, right, you have to stop the program before the battery got exhausted. Otherwise, your tuning is not right. Because when in a later data point you collect is with less power, that means it's not precise anymore, right? So usually, we need to check everything out at about 20 times before, right? So how do we make things converge in 20 times? So then we have to try a lot of technology, which called binary search, like right? You have to do binary search at each dimension, right? 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 And binary search still have a limit. Do you know why? Because binary search, you have to set a range. If your searching range is outside it, you never get it. Right? Right? Okay. So then we will teach you a lot of like optimization problem, like a Newton's method, right? We're going to teach you how to use partial differential function to make things. Okay. So it depends on how fast you can get it. Okay. We will push the level. Don't distract people. Okay. All right. Basically, we push the level as fast as you can. As long as you can understand, we will push it to like next level. Okay. You will find out the more sophisticated algorithm usually it's better. But if you don't understand the sophisticated algorithm, it's even worse because you don't know how to tweak it, right? So this is in last year we stopped at the PID control level and grid search level because that's the place you guys understand. Okay. Okay, this year let's push as fast as we can. Okay, so as a result, we're going to do a lot of project here. Every one of them needs sort of like a PID control. For example, in the last year, we want to implement. Do we ever try to self-balance robot by two wheels?
No, I remember we talked about it.
Yeah. Do you know how to do it?
You said like use a gyroscope and a feedback loop.
Mm-hmm.
Yeah.
Yeah.
We managed to balance it on 3 wheels. Well,
Okay. Okay.
we can do that with a tricycle.
Okay. So, and we after you guys master the get understand how to tweak parameters, then we will go to the robot navigation side, right? First task you need to do it is make the robot travel in rectangle as fast as it can, not just make a robot travel in a rectangle path. Do you know how many PID control going to be there? What? All right. You need to write a PID control to move, stop and go, move at exact distance. This is one PID control, right? Right? Then you need to turn 90-degree. Another PID control to make a turn, feedback loop, right? Right?
Gyroscope.
And another level of it is you need to have a smooth crank up and speed and stop, right? Right? And you have to use multiple sensors because when you do rectangle, every turn you will make some mistakes. And do remember, angular mistakes accumulate very fast. So if one turn is missed by 1 degree, after make a couple rectangle, your robot will probably go out of whack. So right? It's not rectangle anymore. You probably go triangle, whatever. It's not going the path anymore, right? Then we need to use multiple sensors to correct it. How do we do it? Okay, there's another gyroscope and accelerometer in the cell phone. Okay, we can use the cell phone capability to. So do you know why the cell phone know how many steps you run,
My mom cheats, so it does this with her Apple Watch.
right? Do you know why the gyroscope know how many stories you're going up?
Um,
This is the integration, the magic of the integration, right? Because when you go upstairs, there's a delta in the acceleration. If you use the acceleration times delta t, you know overall you're going up, right? Got it? So basically we use the same technology in a cell phone to basically another sensor to back calculate you are in the right track. Okay, not just totally count down the wheel encoder. Okay, so this will help dramatically help us solve the problem. Say either like the wheel doesn't turn, or because of different attraction in the field, we go different distance. Right? Right? Got it? Okay, good. So, and after that, okay. Hey guys, focus. Okay. So after that, we teach you do a lot of fancy operation. Say, give you two ultrasound sensor. How do you make a robot follow a wall? How do you do it? Huh?
You can make it so that the robot runs into the wall sideways and move forward, but you have to set your gyroscope to see that if it turns any to the negative degree, you turn it back.
Oh, what I'm saying, you don't use a gyroscope. Use a ultrasonic sensor. Use distance sensor. Huh? What do you say?
So what if it turn on the back and then detect the wall?
Yes. You put one ultrasonic sensor on the front. Put one ultrasonic sensor on the back. Keep monitor the distance and make adjustments. Right? Those two distances have to be the same. Right? If it's too far away from the wall, you need to side move to close to the wall. Right? If it's tilted, then you have to turn it. Got it? Last year we played dumb. Last year we played dumb, right? We basically have to smash into a wall enforcedly to make the robot go straight. Right? Right? But it's slow. If you have a sensor, why you need to do that?
Like gluten free. How did gluten free do so well?
Right? There's a multiple way to, right? So there's a lot of trick we can play to save time. If we can follow the wall by ultrasound sensor, then we don't need to bend into the wall and move forward, right? We save a lot of time, right? Got it? So, and
How many can you plug in?
huh?
It's the limit.
The limit of sensors that you can put it on is the limit of sensors you can plug in.
Yeah.
Well, which doesn't have that much.
They don't have a limit to the sensor. You can do put as many as you want. Okay. 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 Actually, okay. Hi guys. This is more advanced things this year we need to do. We need to we will teach you how to remember the robot movement and replay it. Remember in last year you see like either gluten free or something, the robot just going squeak, right? They didn't use any sensor at all. Do you know how do they achieve it? They basically push the robot in the past and memorize how the robot moves, right? Then you just replay it.
So smart.
Just replay it.
Oh, it's like those windy toys where you like roll forward and it like gears up the wheel, the
Yeah.
spring, and then when you release it, it just goes.
No. This thing is basically memorize how the robot moves. Just replay it.
Like
So
an encoder of readings.
yeah.
And all the readings
And
from the sensor.
yeah, all this, yeah. For example, it's really hard to do a path finding, optimize the path, right? But our human knows. It's like the gluten free. How do they do this? Do this? How do they do that? They, yeah, they just.
So they just do this, right?
But how did they do it? How did you think they did with the?
Because they could put minerals in the land during autonomous. So they do that too.
Oh, that's a separate technology. Okay, so
But to be honest, that might be true. I don't know what exact program it is, but that seems accurate because like the way the robot moves is like something. Yeah, it seemed like a human movement. It's super smooth.
yeah, so what they do it is they turn off all the motor power, and and then when you push through it, it memorizes the encoder values. Okay, and the gyro.
Tweaking though.
Huh?
They still need to do a little tweaking.
Yeah.
Sometimes it slips a little.
Yeah. So this is the easiest way because the human is smart. You can find the best way, pass by yourself, right? Right? So this is the stuff easily improve the performance. And we don't Yeah, because if you want the robot to figure out everything by itself, that takes really long time. Okay.
And why did no one else do it? I think data force.
Yeah, the data force did it.
Yeah.
Data force was also very smooth, just went right around the laser.
Yeah.
But I observed that nobody at Detroit except for had that. Maybe they didn't know how to do that. Yeah, they probably did.
Yeah. Okay. Basically, if in this summer session, because those programming, there's a lot of work to do. Okay, depends on your programming level. You can start with the easy one. Okay, advanced programmers do challenging ones. Okay, so and this is all the building blocks we are going to use in next season. Okay, so when the if you guys can do all of this in this summer, when the topic got released, we can just quickly assemble a code and go. Got it?
Still need to finish designing it.
They get finished next month.
Right? So basically, right? Okay. So so we spend a lot of time to talk about a plan. So let's spend a little bit of time to say, you guys pick the robot. Oh, to give you like a 15 minutes. We need to form a five squad team, 5 or 4. It depends on you. Okay, 5 or 4. Okay, squad programming team. Okay, you guys pair up together. Pick a robot. Use your host robot, and you stick to that, and do the programming in the whole summer. Okay, let's stop the recording. So. Okay.
Okay, let's choose.
Okay.
Okay, Andre,
Okay.
let's use our robot that
Yeah.
actually finished.
Okay.
We are done today.
Done. Yeah, yeah.